So I guess now it's time to introduce our first keynote speaker, and you know, I will be short because he asked me to do it in a pretty quick manner. So the first keynote is from Professor Marco Gori. Of course, I want to thank him for being here today. You know, what can I say? Professor Marco Gori is a professor of computer science, working since many years in the in AI machine learning. Is working at the University of Siena, Italy, and you know, he works in he contributed to many seminal and foundational works on neural networks, and not only neural networks. That's, you know, just to mention one of them, graph neural networks. And today is here to present his activity on this framework of Cognidynamics for lifelong learning. So yeah, I promised to be short. That's what I did. So welcome to Professor Marco Gori. Nice great.
Yeah, so thanks a lot for inviting me today. This is a very interesting conference. I think, you know, it's covering most challenging topics in nowadays in machine learning. At least that's my feeling. I think, you know, lifelong learning is definitely one of the most exciting research activities for, you know, my understanding. So today I will, you know, talk about, you know, this idea, this general idea on how we can essentially think of neural propagation schemes. But before starting, I want to, you know, say thanks to a number of people who in different way, you know, contributed to originate this framework. I remember, for example, very, very interesting discussions in a couple of workshops that I was organizing a few years ago. One was a new RIPS workshop, and especially another one on biologically plausible learning. So I remember very interesting discussion with, especially with Tishby, with Tommy Poggio, with Joshua Benjo. I think, you know, they contributed to pose a number of questions to me and you know, to elaborate what I'm doing. But of course, most important contribution comes from my lab, and I want to thank especially, you know, PhD students, in particular, Michele Casoni, Tommaso Guidi, and also Professor Melacci and Alessandro Betti from IMT Lucca. So let me tell you about what is my let's say, humble view of the explosion of artificial intelligence. You know, it's a great time, right, for people like us, because everybody is talking about artificial intelligence. And so one interesting question that you can pose is why artificial intelligence has become so important. So here I did my best to indicate, you know, the process, right, since the conception of artificial intelligence. But, you know, there is quite a, by and large, people believe, and I think, you know, there are a number of reasons for believing that it's so important, you know, to think of, you know, the last decades, well, probably deep learning has been, let's say, the subject which contributed most. And recently, these generative AI frameworks are, you know, so important for what, you know, for the evolution of artificial intelligence. But, you know, this is true for sure. And clearly, computational resources and at the same time, the possibility of accessing huge collection is going to be the secret of this success, right? But I want to tell you something which, of course, is only my humble view, but I think the actual breakthrough from a truly scientific point of view, I think, you know, the popular book by Thomas Kuhn, on the structure of scientific revolution, a book which was published, as far as I remember, in 1960, something like this. Well, I think a very important contribution came from what sometimes is called the Connectionist wave. So a number of people that, especially people from the parallel distributed processing research group who began to elaborate a completely different way of thinking, which was in fact that of using neural networks. And still talking about the motivation for this talk, a few years after the explosion of the Connectionist wave, a very nice paper appeared on Nature by Francis Crick, the Nobel Prize on DNA, who published a nice paper on what he called the recent excitement about neural networks. So look, in his own work, the remarkable properties of some recent computer algorithms for neural network seems to promise a fresh approach to understanding the computational property of the brain. Unfortunately, most of these neural networks are unrealistic in important respect. And this activated a lot of discussion, right? It was referring primarily to backpropagation and to the plausibility of backpropagation. And, I remember some discussions, especially with Tommy Poggio, about, an opportune analysis of what also Francis Crick was saying about plausibility of backpropagation. But of course, even before talking about biological plausibility in backpropagation, there is, just an earlier step, because this is the typical neuron of multilayer networks. And clearly the question is, where is time here? There is no time, right? So you can use this formula in a sort of algorithmic framework, but there is no time. So if there is no time, this is not plausible from a physical point of view, because the signal, has a certain velocity, right, in the transmission. And so this, is one important thing, right? What about time? And let me show you this picture just to understand better why I think we are still missing something important concerning neural propagation. So this is a classical, deep architecture where you see the input, the layers, the output. And suppose you are processing a stream, for example, a video, and you are processing at different steps. And let's assume that you have a supervision at each step. Of course, you may have also a Lagrange, a loss term, which, offer you the supervision, for example, in different framework, like unsupervised learning, right? What is important is that in backpropagation, sometimes we don't focus attention on a very interesting problem which has to do with time. So if you really want to learn here, what you have to do is that you have to forward the input, and then you have to activate a backward step until you reach the first hidden layer, right? But during this computation, the input is kept fixed. You don't move the input, right? So you have to wait until the forward and the backward step ends. So what about something like this, right? You assume there is a forward step for the computation, for the activation, and a backward step, you see, it's a sort of wave, right? So you have a delay, and step by step, what you do is that you calculate, you see the blue is referring to the forward computation of the activation. So there are neurons, after a while, which contain both the forward and the backward step. And then you can actually compute the delta error. You have the delta error available, you have the input available, and you can calculate the gradient, okay? And of course, this is nice because when the pipe is full, okay, so apart from the transient step, then you have this wave which make it possible to compute directly the gradient. So if you go back to the comment on plausibility, here you have a sort of local computation, right? And the computation is local in space, but it's local also in time, okay? Which were, you know, this had to do with the criticism of Professor Crick, okay? So today, I'll do my best to tell you about something which, for my understanding, was left a little aside by the connectionist way. And what was left, I think, a little aside is time. So what happens if you have a neural network and you want to learn by considering in the very beginning that you are processing temporal information, okay? And so I call, so it's a sort of theory for describing neural propagation, which, you know, begins from interpreting time since the very beginning, okay? And before entering the details, let me show this picture, right? This is a slide which comes from the popular Norvig and Russell textbook. So the most popular textbook in artificial intelligence. So if you look at the topics of artificial intelligence, it's pretty easy to create two clusters. So you have those topics, you see the green cluster, like knowledge and reasoning, problem solving, for example. And then you have all the topics which are related to machine learning, right? There is a big difference, right? The big difference is that if you look at this symbolic AI, you don't really need to collect data. At most, you collect knowledge, right? So you have knowledge, which is a completely different story, right? So no problem of privacy, you know, it is knowledge. Whereas on the opposite here, we need data. And we have seen that the impressive results that we experiment nowadays are exactly because we have the possibility of processing huge collections, okay? So what about the following challenge? Why not to unify this cluster and think of a theory of learning where there is no pink cluster anymore, right? Everything is green. Everything is assuming that you don't need collections for learning. So no data collection, which seems to be a bit strange, right? Because nowadays, the success of machine learning and overall of artificial intelligence is due to collection. And interestingly enough, we had to wait for the web to become official after, you know, the 6th of August, 1991, when Tim Berners-Lee published the, you know, the indication for accessing the web for, you know, later on to see the explosion of artificial intelligence. What if you assume that you don't need collections anymore? So let's explain better what I mean, right? So the challenge can be simply described in this way. Suppose you are given an agent, you know, this is a typical, you know, picture, once again, coming from the popular Norvig Russell book. And, you know, there is this agent which is interacting with the environment, okay? But what is interesting here is that, of course, you access data, right? Just you, like you, right? Just like animals, okay? So during perceptual interactions, everybody is processing data, but none of you is recording the signal, right? So during this presentation, you will create in your mind a very deep, abstract representation of what I'm telling about. But of course, there is no recording of the video, right? There is no recording of things which are not important for you, right? So at the end, you will create a very nice abstract representation, very compact abstract representation. And in principle, you don't you don't need to store data, right? You simply need to access data at the current time, this time, right? But you don't need to store data. So what happens if you change everything in this perspective, right? So you can think of, robots which become, in a sort of musician life, right? And you can think of, these robots which are exposed to music, right, since the very beginning. And of course, they start, in principle, they can start listening and parroting, and later on, they can react to evaluations, right? Because you start playing and somebody will tell you about what happens, right? Whether it was good or not. And of course, you will have also to decide when the times come for you to play, right? So you are continuously in this musical environment, and it's a sort of artificial life, which means that you have also to decide when the times come for you to present, right, to expose yourself to the judgment of other people. So what could be the methodological approach for processing, for thinking of a new theory of neural propagation, which incorporate time, right? Because, what we were mostly missing was time. Of course, we have a hidden Markov model, we have recurrent neural networks, but if you will see at the end of my talk that there is some important differences in this notion of time with respect to what we consider time in hidden Markov models or in recurrent networks, but also in reinforcement learning. So time is something which is commonly used in, for example, in physics, and one possibility in those disciplines is that of creating and devising laws which arise, and this is very interesting, from the minimization of functional. So, for example, in theoretical physics, we know that if you minimize the action, then the minimization of the action produces the Newtonian laws. So essentially, there is a very well-established extension of calculus, the so-called variational calculus. The Euler-Lagrange equations, simply correspond to the Newtonian equation. And so I was thinking of establishing the following relationship, right? So in general, you assume there is, think of a sort of abstract description, right? This is abstract. You have a functional, and you can try to bridge two things, right? The laws of mechanics and the laws of learning. In mechanics, what we know is that there is a sort of kinetic term, and there is a regularization term in machine learning. Then you have a potential energy, and the associated term is the loss function, right? So you see, there are some analogies, right? So what about capturing the regularities in learning, just like, what people normally do in physics, right? You capture regularities. And so my intention here is to see what we can do. Well, there are some differences, for example, this sign, but, from a truly mathematical point of view, there is an interesting analogy, and there is something that if you look at the, from one side, you have the position, the velocity of particles, and with neural networks, you have the weights and the velocity of the weights. Then you have the conjugate momentum, and you have the conjugate momentum for the weights. So you can think of particles and weights. So you have big systems, for example, in theoretical physics, and you have big neural networks, and there is time, and there is this issue of neural propagation that we will see. What is interesting is that we can use the same mathematical apparatus, apart some differences that we'll see in the next few minutes. So look at what is the transition here, right? This is the classical functional risk that you can check at the very beginning of any machine learning textbook, right? So you have the loss function, and you need to measure the loss function by using a probability measure, right? So you have a probability measure, join probability distribution between the input and the output. But instead of creating this average using probability, and so using collections, what about, summing up the loss over time? Of course, it's an average, just like this average, right? The only difference being is that you don't need to collect data, right? What you have to do is that you have to devise a theory in this framework, right? And in this framework, there are analogies, but for example, this is called, Lagrangian instead of loss function, but, the principle is more or less the same. So let me show this slide that I think is likely one of the most important for telling you what a theory on neural propagation could be, right? So here I'm describing a potential model of recurrent neural networks. Many people in the area of machine learning used to see discrete time models, right? But for the sake of simplicity, I'm using the continuous setting simply because it's more compact and I would say elegant. And then you can easily rewrite in the discrete time framework the equations. So what you see is the typical propagation that you have in neural networks. So you see the weights, the weighted term. And then you have, if you look at psi dot, means the derivative with respect to time, right? And the derivative with respect to time, once you approximate in a discrete setting, of course, you reproduce the traditional recurrent neural networks models. So this is quite a classical model. There is only a big difference here. You see the weights are calculated by using this gating mechanism, right? So you have some gating parameters, these gating parameters, and we assume that we control this variable nu, okay? So this is the weight. You see, this is the velocity of the weight. So instead of moving the weights, we move the velocity of the weights. But, it's not so fundamental. And of course, just like in traditional machine learning, what you have is the kinetic and the potential energy. This is a sort of regularization term. This is a sort of potential, right? You have some gating terms, but apart from the gating terms, you see there is an interesting analogy. You have environmental interactions, but what is important is that in addition to the traditional framework, there are some parameters. So look at the parameters that I'm here enhancing. You see these parameters, I call this parameter dissipative parameters. For example, they are gates of a neural network or parameters which can filter out also the error, right? And this is important because, for example, one thing that you realize as soon as you are in this framework is that, well, at the very beginning of learning, there is a good chance that you need to be protected, right? Instead of being exposed to all the information, there is a good chance that this dissipative parameter has to protect you from the exposition of a lot of information, of a lot of error, right? So there is a gating mechanism which, as you will see, comes in conjunction with the basic theory. So we have new coordinates for learning, right? And so what is the solution of this problem? Because now, let me tell you something that, you need simply to be patient enough to study, the framework of optimal control, which is, very classical, optimal control and differential games. There is a very well-established theory. And, for all of you the main, let's say, intuition behind the theory is that it is based on dynamic programming. So classical stuff for computer scientists. And so we know what is the solution of the optimization problem. Remember the framework of theoretical physics, right? You have to minimize the action. And here, likewise, you have to minimize, remember, the functional risk, which is a sort of action, right? What is interesting is that we know very well in theoretical physics, so there is a very good and developed mathematical machinery for solving these problems. And interestingly enough, you know, the solution, the solution can be offered by using the Hamiltonian of the system. You will see in a few minutes what it means, right? But look, this is the state of the neural network. The state contains the response of the neurons and the weights. So these equations tell you how the state evolved and how the co-state evolved. So what is the co-state? The co-state is essentially playing the same role of the state, but since the state, you know, is giving you the information from the past, and the co-state is somehow offering the information from the future. One interesting thing for you to know, you will see in a moment, is that the co-state corresponds somehow to the delta error of backpropagation. So we will see in a moment. But what is important is that the theory tells you that the co-state, if you want to optimize, has to go to zero, right? But of course, the theory for the optimization assumes that you need the collection, the entire collection, right? So you give me the entire collection, and there is a theory for optimizing the function, right? But of course, in machine learning, and especially in the framework I'm proposing, where you don't have the collection, you have to do something more, right? What is nice is that these differential equations here, you know, this means a partial derivative, okay, with respect to x, and partial derivative with respect to p. What is interesting is that in any case, these differential equations are general, right? And you have these additional parameters. But now, what is the Hamiltonian? So given the neural network, the Hamiltonian is just a way of combining the neural network and the environment, right? So given the structure, the architecture of the neural network and the interaction with the environment, you can essentially create a mathematical object which is representing, you know, the neural network in the environment. And the theory tells you that you have to minimize with respect to the control variable, and you can essentially, given the recurrent neural network in a given environment, the Hamiltonian, at the end, you see the Hamiltonian is a function which depends on the state and on the co-state, and on all the other variables, learning variables. But now, let's look at this slide because, you know, now you see how interesting is the impact on neural propagation, right? So this is a classical recurrent neural network. You see, you calculate the state. So this is the variation of the state, okay? So this is the variation of the weights. You have some gating parameters here. And during this computation, you need the parent of, you know, the generic unit. And concerning the co-state, look at the co-state, right? Oh, this equation comes simply from the Hamiltonian, right? So you simply have to, you know, you have to be patient enough doing the calculation. You see that the state depends on the parents, and the co-state, you see, comes from a sum which is accumulated over the children. This is exactly what happens in backpropagation, right? And if you look at the structure here, you see, this is the typical structure of backpropagation, right? This is the prime derivative of the activation, and you see the backward propagation. But the backward propagation is local. a time t on that neuron concerning the neighbors of your unit, okay? So as I was telling you, the co-state is a Lagrangian multiplier, and at the end of the day, the message for neural computation is simply that is the generalization of the delta error, okay, when you consider time. So let me now go again to the previous slide. So remember, I was thinking of a sort of, I invented a sort of forward and backward way, right, for gaining the local propagation. What is interesting is that this theory is essentially telling you that you have a forward and a backward step. So I'm just repeating the equations again, which involve parents and children of the node, and everything is local, right? So at the end of the day, for what to the best of my knowledge, this is a way of attacking a long standing problem where you want to obtain in recurrent neural networks algorithms for computing the gradient, for example, which are local in both space and time. There is a possibility, for example, of having such a computation where you have only local connections. But in general, if you have any architecture, to the best of my knowledge, this is not very clear. And this theory tells you in a very simple and straightforward way how to calculate everything. Well, this is just to show that this is really entirely local, right? So you may have a loop over time, and then you may consider the loop on the units. And what is important is that you have tensors which are updated locally in space and time. So let me quickly tell you connections of this theory, for example, with gradient computation, right? Or look at this equation, right? You see there is a sort of learning rate. So the Hamiltonian equations tell you that there is a sort of, generalization of the traditional weight updating equation. And there are a number of properties, but let me focus on this property here, right? At the end, we can derive how the weights change, you see? And the second order equation, look, this is the prime derivative of the co-state, right? And what is the prime derivative of the co-state? So let me just, first of all, right, this is a sort of generalization of gradient-based learning, but look, for example, at this equation here, right? Remember, when we derive backpropagation, the computation of the gradient comes from the classical chain rule, right? And so what you have is that you have a factorization of the delta error and the output of the neuron. And you see there is the same symbolic structure, even though this doesn't come from gradient descent, right? So this comes from this general picture of optimization in time, okay? There are some interesting things which motivate why I call the previous parameters, these new parameters, I call dissipative parameters. For example, quite a simple and straightforward consequence of the theory is that we can express, once you define the energy and the environmental energy, which is essentially the energy which comes from the environment and interact with the learning system, then you can define a dissipative energy. And you see that dissipative energy depends on the square of the velocity, okay? Traditional dependency in physics, for example. Well, we end up in a theoretical statement, which is quite a straightforward consequence. As I told you, this is a very well-established mathematical apparatus. You don't really to reinvent important things, right? You simply need to be patient enough to see the derivation, right? And one important thing is that there is a sort of what I call the first principle of Cognidynamics, simply because you can immediately interpret what happens in a neural network which is learning, right? And the interpretation is that the environmental energy is dissipated by the learning process. You see, the objective is that the Hamiltonian has to go to zero. So there is as you can see in this equation, there is an internal energy, and the purpose of learning is that of decreasing the Hamiltonian. So the generalization is expected to achieve also, think for example of the definition of loss functions like the entropy term. What you can see in addition is that the entropy is, of course, during learning, is expected to be reduced. So now, before concluding, I want to give you just a preliminary idea on, a second important part, because so far, there is nothing really new apart from, the actual adoption of this theoretical framework from physics, right? But there is a problem here where you can see a remarkable difference with respect to many physical systems that I know, right? And the big difference is that, maybe can very well summarize in this statement, right? So essentially, we possess the differential equations, or if you like, the recurrent equation for attacking the problem, if you give me the entire collection, because I have to satisfy the boundary conditions. So nothing really new, because my introduction was, what about learning without collection? And now I'm back to collection, right? Which means that it's not such a good business, right? So where is the business, if any? Well, you have to be able to reuse the same theory. We know that differential equations are exactly the optimum, but the problem is that you have somehow to guess the initial condition, and this is, of course, very, very difficult. So what should you do? You should use the these parameters. They are, the parameter that I call dissipative parameters, and you can think of two different ways of learning. From one side, you have this theory of optimal control. So it's one direction, right? And the optimal control just reproduce in this more general setting the gradient computation, right? But then you need to move also, suppose you're at the generic time t, okay? So you need an additional direction, right? You need to learn those dissipative parameters. So the idea is that focus of attention mechanism are extremely important. And these parameters are exactly the parameters which decide how to expose the agent to the environment. Because, otherwise, these differential equations are typically unstable. And just to give you a message which is quite popular in the community of machine learning, you may remember unstable behavior in recurrent neural network. There is a seminal paper by Simard, Frasconi, and Benjo on long-term dependencies, right? And, the seminal paper tells you that you may be in front of unstable behavior if you want to keep memory, right? So it looks like you need a sort of gradual process in order to have, to develop abstract representation of the world. And this is what is missing in my understanding. So what is actually missing is this learning direction. What we have to do is to learn gradually. And there is, in fact, a heuristical approach that you can use, because the co-state, that the co-state as a boundary condition has to vanish. And this is what can drive the learning scheme of these new parameters. Just to give you an insight of what it could be a possibility for learning, this is the typical, the prime derivative of the co-state is, in my understanding, the most similar object with respect to traditional machine learning. Is the gradient, essentially. Don't forget the factorization. You see, the factorization of the co-state and the state, okay? So once you see, this is the gradient term, what can you do? Can we actually see if this gradient term can decrease? Well, supposing you can easily see what happens, right? You can, from this equation, you can promptly, you see, derive what could be the change of the square of this term. And of course, you very much would like this term to be negative, because it means that this is a good heuristic for the decrement of the square of the co-state, right? But don't forget that here you have some parameters. For example, this parameter here, this is a dissipative parameter. This was not the parameter involved in the optimal control strategy, right? This is an additional parameter. So we are essentially, remember, I was, in my acknowledgement, I was mentioning, for example, Professor Poggio. I remember some discussion with Tommy Poggio, and he was claiming, I don't know whether he still is claiming, that one of the major problems in learning, for example, with backpropagation, is that you have the same circuit for the forward and the backward step. So you need a sort of matrix for the forward step and then the transpose for the backward step, which he said that this seems to be also a bit unreasonable. And what if you have additional parameters? So these parameters are new parameters for learning. And essentially, the intuition is that those parameters are the parameters which are driving the extraction of, let's say, abstract concept. So in a sense, the principle is that you can play with this parameter in order to decrease gradually the co-state. So for example, here, you can simply use flip the sign in case this condition is not verified. So don't forget, you have essentially, going back to the previous slide, remember you have two coordinates of learning, the traditional weight updating and this new parameter. So let me quickly conclude, but before concluding, notice that, of course, as soon as you prove that this co-state goes to zero, if you look at the evolution of the weights, well, you have an equation which is indicating that you can get a constant solution. So, okay, let me, before driving conclusions, let me tell you some of the topics that are covered and we are covered so far. We have mostly covered, this part. So the construction of a sort of causal optimization, which is classical from one side, but there is a novelty. It's the introduction of these new parameters, this new circuit, which is used for the gradual learning. But of course, as soon as you study neural network in this way, you can start thinking of architectures where you do not necessarily have layers, right? Maybe you have some layers, but generally you have a very complex structure. And, it's not a deep network, right? It could be a big network, okay? But the structure could be very complex and sophisticated. And what is also interesting is that as soon as you think of machines which don't play with big collections, but simply interact with the environment, you can think of small machines, right? Small devices, which do not necessarily use cloud computing, right? They can be regarded as agents which live in their own environment, and of course they have to take a number of decisions which are crucial, and so there are also some crucial issues of consciousness. There is a big challenge that we are now facing in the lab, and is what is written there, right? So major challenge, don't rewrite on weights which are already contributing to solve previous task. This is a fundamental question, I think, for most of you, or maybe for all of you. And of course, now what I was telling you about is a new neural propagation scheme, but in no way there is a specific indication that we are not still exposed to the same problem, right? Interestingly enough, when thinking of the dynamical structure of this neural network, one intuition is that without changing the theory, so reusing exactly the same theory, you can think of models, and maybe this can be used also in different frameworks, where the major assumption is, I had an idea, think of gravitational interactions, but gravitation is not necessary, but think of gravitational interaction, right? And think of neural networks which are composed of recessive fields, recessive fields are important, right? In neural computation, think of the recessive fields of convolutional network. So you have recessive fields, groups of neurons, and you think of interactions of those recessive fields, right? A sort of gravitational interaction. One interesting thing that we could do is that we could drive the state according to a gravitational interaction, which means that, for example, this recessive field here, think of this recessive field as a body, okay? Then you have the n-body problem. You have many bodies, but of course, there is no interaction if the bodies are very far away, right? Of course, the solar system is using there is a very nice structure in the solar system, and it doesn't depend on, let's say, bodies which are in another galaxy, right? And this is nice because it means that if you create some structure, right, they are stable, and once they are precious, you don't rewrite on this structure. So we can reuse the same theory essentially for these models. And other things that recessive field that we can easily incorporate because the framework of the Lagrangian is very well posed for this idea is, for example, you can think of recessive fields where you have the natural principle of, let's say, injecting hidden semantics, right? So for example, any Horn clause can be injected in a Lagrangian term by using the triangular T-norm. And so you can think of architectures where, you have, let's say, so where you have different recessive fields where you injected these latent semantics, which could become at the end also semantics which make sense from a linguistic point of view. And finally, so this is my last slide. Well, I focus on this optimization model, which is an agent. But as I was telling you, since this agent lives in a temporal environment, it makes sense to have a sort of consciousness model which control the operation of this model. So for example, you see there is a gate in here. It can, decide when the time has come for delivering the decision. And of course, there are some interesting things that this module, which involve conscious action, can take about the Lagrangian module, right? Finally, let me draw a few conclusions. What I presented today is essentially a theory for neural propagation, right? So essentially an attempt to look at the great perspective that was offered by the Connectionist wave many years ago, and trying to analyze, what is probably, at least in my humble view, what is the most serious problem. The most serious problem, something which, in my understanding, was not solved, is that there is no time right? So there is an emphasis on collection. And what if you forget collection and you process information continuously, right? Um, One of the major results nowadays is that, at least as yet, is that we have a local space and time propagation. So there is it's possible by using this pre-algorithmic framework to devise algorithms which are local in both in time and space. And there is this suggestion about a sort of new learning circuit, so additional parameters for controlling the behavior of the network. And as soon as you see this green here, right, this is our wishes. We still have to study what could be the impact of using architecture, general architecture, so not necessarily layered architecture, right? Because there is no need to think of layered architecture anymore. And finally, the last but not least is that this is open the doors to thinking of small intelligent systems, so small agents, which primarily interact in a social framework, so interaction between agents and interaction with humans. But the measure, so from one side, there is a scientific challenge, and the technological challenge is that you may start thinking of intelligent systems which don't need the cloud, right? So that's the transition. And of course, this has nothing to do with what I presented today, right? In what you do, right? This is also an invitation for all of you to start thinking of an orthogonal direction, which is not necessarily that of reinforcing what sometimes I call the dragons, okay? So thank you so much for your attention.
Okay, thank you very much, Marco, for this presentation. We have some minutes for questions. Are there any questions from the audience?
Thank you so much for the talk. It was really interesting. I'm just trying to understand a little bit better and connect it to the things I know. So I've seen people trying to speed up gradient descent by trying to propagate the backwards and the forward at the same time. So there's a paper, I can point you to it. It's always seen as an approximation, as a trick that they do just to reduce latency, not as something proper. And they try to compare to gradient descent. But my question is, in this works, for things to work, the assumption is that there's a lot of correlation in the data. So I'm wondering, in this framework, is there any assumption on the environment that sort of the way that time goes, there's actually a lot of correlation in sort of the observations that you get from the environment for learning to actually progress? Because otherwise, I think it will break down, right?
Yeah, I think I can, that there is a very, straightforward answer. There is no assumption at all. Essentially, the locality, the spatiotemporal locality is just the outcome of using the Hamiltonian framework, which in a few words is, let's say, it's a sort of, analogy for the computation of the gradient, right? But the secret in the computation of the Hamiltonian function and the derivative, let's say the difference and the secret is simply that the Hamiltonian involves at the same time the spatial connections and time. And as soon as you calculate, the prime derivative of the state and then the co-state, which is essentially the delta error, you gain this locality. And this is general, right? And this is, I think, for what, to the best of my knowledge, you know, I was interested for years in trying to understand locality and the possibility of avoiding, right? For example, the forward and backward step. But I think, for example, I didn't know, I was not aware, and I'll be happy to see the paper, right? Yeah. But maybe there's some assumption. No, here there's no assumption at all, right? So it holds true whenever you have a model of your agent in the environment by using the Hamiltonian, which is general.
Okay, can I maybe rephrase the question to make sure?
Sure.
So like if time doesn't exist for the environment, so the environment is just mapping random numbers, this will still work?
Random numbers?
Yeah, so the environment is like you just map some random numbers to other random numbers. There's no structure to it. Then this has to break, right? There's no, like the assumption is the environment exists within time, the same as the agent, and there's therefore some kind of temporal correlation or like temporal smoothness.
Well, yeah, that's important, right?
Okay.
It has it has to do. It's a good point, right? It has to do with. I was telling during my presentation, I was presenting the continuous set, right? In the discrete set, there is exactly the same theory, right? So the same theory with Hamiltonians. But of course, if you have random numbers and random things to capture, you can likely understand what happened, right? Nothing will come of reasonable in terms of learning, but still the computation is local. Maybe it's not meaningful, right? But it's still local because this property, which holds for the continuous set of computation, have a dual in time discrete computation. I simply presented the continuous setting because it's more straightforward.
And then sort of the last question on the gating on the gradients that you have. Is it okay to think of them as a preconditioner for gradient descent that is like an adaptive preconditioner? And would that help me like derive assumptions that I need to have on this control signal? So for example, for preconditioner, we know it needs to be positive definite. So then this gives you an idea of how this gate should behave. Does that make sense or not at all?
Yeah. Well, these parameters, like the gates, for example, are parameters that I introduce simply because you know the problem with this optimization is that, as I was saying, it is formally correct whenever you have the big collection of data, right? So again, it means that you simply reproduce instead of the functional risk, you are in a different setting with the same problem. The introduction of gating parameters, for example, is what you know, enables another learning direction. So the theory of optimal control is simply used for driving the weights of the neural network, the traditional weights. Whereas, you know, these new parameters, which are essentially gating parameters, do require to control the co-state at the end. So the heuristic is that you have to keep the co-state small because otherwise there is an explosion. Remember, I was mentioning, you know, this study, which was already pretty well known, right? The problem of instability in recurrent neural network learning.
Okay, thank you.
Hello. Maybe I'll just introduce myself. I'm one of the authors of the PDP books, Jay McClelland, and I've been interested in these kinds of dynamic issues that you've been talking about extensively in my own career. We had a paper in, I believe it was 1996, in which we used the continuous time version of recurrent neural networks that I believe you were describing, and I believe exactly the whole dynamics of learning that you were describing for training the weights in that system. And we, you know, I visualize these unrolled networks in the same way you do, I think. So I never studied physics, unfortunately. I'm learning about these things later after I'd finished all my formal schooling. So I don't understand all the equations, but there are a couple of things about the second part of the talk after you talked about that backpropagation stuff, and mostly about these, I guess, these stability enhancing things and stuff like that. So these things that you were talking about remind me of very common things that people use in machine learning. And I just want to know if you are familiar with them.
Which use where
in machine learning.
Okay.
Okay. So the two ideas that I'm going to talk about are, first of all, I'm blocking on his name right now, but the most common way in which we adjust the gradient parameters in backpropagation uses a second order rule, which is changing the, keeping track of the variance of the parameters in of the gradient. Okay, so if the variance of the gradient is high, you turn down the learning rate. Okay, and that is the most commonly used sort of smoother of the gradient in propagation. So, this is extremely widely used. It's Jimmy Ba's rule, and I just can't remember its name. Somebody else in the audience ought to be able to help me with the name. Adam, thank you. The Adam optimizer. Are you familiar with Adam?
Yeah. Okay. Yeah, well, if you look at, for example, this equation, right? This is essentially the closer equation to gradient descent. As I was saying, this is essentially the gradient, and you can see the structure of the gradient in the factorization here, right? You see the delta error and the output in the presynaptic connection, right? So the factorization of the data.
Yeah.
So there is in fact a reproduction of equations which are really similar. And what is interesting concerning your comment on the variance is that you see there is also this equation which seems to suggest a connection with the gradient, but interestingly enough, the one which is more similar to the gradient, look at the arrows, is the second, this one, which is essentially the one you were referring when you think of, for example, a sort of, also dynamics. What is, by the way, of course, I was mentioning, those studies those early studies in backprop and also in recurrent network. But your question gave me the opportunity to discuss why, we are in front of something different in terms of when we involve time in this way, because we shouldn't confuse the mechanism, the typical numerical mechanism, which seems to evoke time, right, with respect to the actual processing over time, because the agent is interacting with the environment and there is a time of the environment. Then there is a sort of internal time, right? Because the machine has to do its own computation, right? So for what I understand, when I was, let's say, underlying the importance of the PDP studies at that time, right? My understanding is not only in the first way, but also recently in deep learning and in generative AI, I don't see, for what I understand, and let's say, a deep understanding of what happens when you have an interaction with the environment and you consider at the same time the processing of the machine, and it takes a certain time to take decisions, and the time of the environment. And this is where, the theory is trying to give a contribution, right? So in considering time as it is, right? So not the time of the computation of the algorithm, right? But time as it is, and the response at any
Yeah, the world doesn't give us enough time to do all that computation. You're absolutely right. But the second question was, and maybe we can put this out there quickly, but when you were talking about the problem of stabilizing the weights that you used to solve the previous problems, not allowing them to learn when you're learning a new task, that is exactly the problem that elastic weight consolidation and synaptic intelligence and several other algorithms that people have introduced have been addressing. And again, I'm sort of asking, are you telling me the same algorithms that these people are suggesting in their papers, or are you familiar with those papers? And if you aren't, it would be great if you would, connect this work with this work, which is at the very core of what people are doing in machine learning and the foundation of, essentially continual learning research.
Yeah, no, but I think you're definitely right. Interestingly enough, this is a time in which there is also an explosion of new solution, especially, in this framework of lifelong learning. What I can tell you for addressing your question is that I like to distinguish what I call a sort of pre-algorithmic step and the algorithmic step. Because my understanding is that if you really want to deeply understand what happened, at least, for example, in nature, you likely need to interpret these laws of learning, which maybe later on can be interpreted in terms of algorithm, discrete, the typical discrete setting. But in order to fully understand what is the kind of temporal interaction, the intuition is that it's better to begin exactly from the actual frame where the cognitive process takes place. And of course, then when you start writing the algorithm, there is a good chance that maybe we find some close relationship. But the only thing which I think is really different, think, for example, of backpropagation through time. As you know, backpropagation through time suffers from the locality in time. And so people try to do something similar with different real-time recurrent learning. And in that case, you suffer from the locality of space. So for what I understand, this is the first attempt to combine and gain locality in both space and time. But of course, I think you're right. It's time also to check carefully what happened in this explosive literature.
So let's thank the speaker again. I think we are out of time for questions. Thank you, Marco. So now we are going to switch, opening the tutorials. So as anticipated, there are two tutorials running in parallel, one in this room and one, right close to the entrance, basically, of the building, so you can select. In this room, we have the tutorial on theoretical advances in continual learning. So I invite Ite, Evron, and Jin Lee to come here. In the other room, you will have the tutorial on data heterogeneity analysis for out-of-distribution generalization from Peng Kui and Jiashuo Liu.